Hi, I am Alice.
And I am Bob.
Bob, I want to tell you a secret,
Oh, I am curious.
but I'd better encrypt it.
All right. How?
We first need a key for encryption and decryption.
Ah, okay. How do we get that?
We can use QKD,
QKD?
quantum key distribution. QKD is a method for distributing secret keys for cryptography. For that, we use principles of quantum theory, for example, that a quantum state cannot be cloned. To implement QKD, one can use different degrees of freedom of light, such as polarization to encode information.
Can you remind me what is polarization again?
By polarization, we mean the direction of oscillation of the electric field. Look here. In the red case, the electric field oscillates horizontally, therefore we call it horizontal polarization.
I see. And a polarizer then transmits or absorbs the light depending on the polarization.
Yes. Let's use a vertical polarizer. You see, the horizontally polarized light is absorbed.
How would it behave if we added a second polarizer to the system?
Good question. If the second polarizer is aligned to the first, light is transmitted. However, if they are orthogonal, it will be dark at the end. The second filter is absorbing all remaining light.
So there is no light. But if you put a diagonal polarizer in between, some light will be transmitted?
You got it.
Does that mean that a measurement in between can alter a quantum state?
Exactly.
So you can send me a single photon.
And encode information in one of the four polarizations: horizontal, vertical, diagonal, or anti-diagonal.
And I try to find out what polarization you have sent.
Yes, and if some attacker wants to eavesdrop, there is a chance that they alter the state. For example, I send you a diagonally polarized photon. The attacker does not know the polarization direction, so they wildly guess. Say they try to measure and guess the polarization was vertical.
So they measure and send a vertically polarized photon to me?
Yep. Therefore, there is a chance that you now detect my diagonally polarized photon as anti-diagonally polarized, an error that we can detect.
Okay, so you use random polarizations for each photon, and by checking the error rate, we can monitor if someone is recording our key.
Which we then use for cryptography.
And if I am far away from you?
We could use optical fibers. But for long distances, they are quite lossy. So for those cases, I would actually prefer to use a satellite like CuBE. The satellite distributes a first key with one ground station, flies to the next one, and exchanges another key. From those, we can get one shared key for encryption.
That's nice. Thanks for your explanations, Alice.
Hi guys, what are you talking about?
Hi Eve,